Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the drag force and then lift force. We have seen various theories behind the drag force and various applications with respect to the drag force, and then we are discussing about the lift force. So, as we discussed, the lift force is the force exerted along the direction normal to the flow, that is the lift force, and we have also seen that say some cases like say airfoil or the aeroplane is concerned, lift is very much essential and we are looking to get better lift, but some say cases like the design of a car or auto, the design of a bus, we are trying to reduce the lift. So, depending upon the case, we will be trying to increase or decreasing the lift. So, that way we have to see that which way we have to plan, whether say which way we have to use design in such a way that lift should be to generate lift or to reduce the lift. So, that we have to see the case. So, as I mentioned, say for an aircraft is concerned, you can see that the thrust is in this direction and drag is here, and then weight of the aircraft and lift is in this direction, which is say here we are generating this lift so that the aircraft is going up and flying. But as far as car is concerned, you can see that since with respect to the lift, the efficiency of the vehicle will be reduced, so we want to reduce the lift. So, as we discussed earlier also, so the lift force we can calculate say with respect to the shear stress and the pressure force. So, if we consider an elemental area like this, and then if the pressure is acting P into dA in this elemental area like this, and then it has got two components, one is P dA sin theta in this the horizontal direction, P dA cos theta in the vertical direction, and then shear stress is also concerned, we have tau 0 dA cos theta in the horizontal direction and tau 0 dA sin theta in the vertical direction. So, that for this elemental area the lift will be dFL is equal to tau 0 dA sin theta minus PDA cos theta, where theta is this angle here. So now say for the body is concerned, we can integrate with respect to the area, so that the total lift force will be equal to integral upon area A tau 0 ds sin theta minus integral upon area A PDA cos theta. So this is the general expression for the lift force, which we generally use in the calculations and for the design purpose. And then generally the lift is concerned, we can represent in terms of a say coefficient. It is called the coefficient of lift. Coefficient of lift is defined as the ratio of the lift force divided by this half rho u infinity square into A, where this u infinity is the free stream velocity and A is the area of the body area which we consider, and rho is the density. So coefficient of lift is equal to lift force FL divided by half rho u infinity square into A, where u infinity is the free stream velocity. And then say we can see that this lift coefficient is a dimensional form of lift, and then this as we discussed in the case of drag, lift coefficient or lift force also depends upon the shape of the body, and then various fluid flow parameters like Reynolds number, Mach number, Froude number, and also the surface roughness of the body which we consider. So the lift coefficient here is a function of shape of the body, the Reynolds number of the flow, Mach number of the flow, the Froude number, and the surface roughness ratio is epsilon by L. So where epsilon is the surface roughness. So out of this we can see that most important parameter is generally the shape. So in the case of drag also we have seen the effect of the shape as far as drag coefficient or the drag force is concerned. Similarly here the lift force is also considered. We can see that shape is very important. So and then with respect to the earlier expression which we have seen for the lift force, we can see that most lift comes from the pressure force and not from the viscous force. So the major component here you can see this in this expression, this term PDA cos theta is the major contributor as far as the lift force is concerned, and shear stress tau 0 ds sin theta component is a small part as far as lift is concerned. So we have to create or to generate lift, we have to see that there is a pressure difference between the top of the body which we consider and bottom of the body, so that lift is generated, or if we want to reduce the lift, so accordingly we have to see. So and then importance of shear stress or pressure effects depends upon the Reynolds number. So we have seen that here the lift coefficient is a function of shape, Reynolds number, Mach number, Froude number, and epsilon, the surface roughness. But you can see that the important parameter here is the Reynolds number, Mach number, and Froude number. As we have seen in the case of drag force or drag coefficient, the effect is small, but Reynolds number is another important factor or important parameter here. So depending upon whether the flow is laminar or turbulent, or say when the Reynolds number is increasing or decreasing, we can see that the lift force changes. So now as far as lift force is concerned, we can say design devices to produce lift, as we have seen in the case of an aircraft. So that lift is generated, so that a pressure distribution that is different on top and bottom. So if you consider, say for example, an airfoil here, so lift will be, say we can generate lift by having a pressure difference on the top and the bottom. So in a very similar way we can see that aircraft is concerned with the wings of the aircraft, there will be a pressure difference, and then we can generate the lift. And then for larger Reynolds number of flows, the pressure distributions directly proportional to the dynamic pressure. So when the Reynolds number is increasing, that means when the flow becomes turbulent, then we can see that the pressure distribution is generally proportional to the dynamic pressure, or rho u square by 2, and then say depending upon this factor rho u square by 2, the lift generator or the coefficient of lift will be changing. And then also another important thing is that which we can observe, say for example with respect to this airfoil or most of the other designs, say mostly lift producing objects will be non-symmetrical, or we have to design such a way that this non-symmetry or the object is shape or it is designed in such a way that it is not symmetrical. So that way, say more lift will be generated. So, this is a typical case is this airfoil. When we put it at an angle of attack, we can see that the lift will be more. So, some of the other practical examples as far as lift is concerned, we can see many real life cases. We can observe the phenomenon of lift. So, say for example, when we spin the spherical ball in the case of cricket, golf, table tennis, etc., lift will be generated. So, this we will be discussing later, say which is the effect, so called Magnus effect, we will be discussing later. And then of course, the flying of aircraft, which is we can see observe in the case of an airfoil, say, and then a projectile motion, and even say in the case of swimming. So, while swimming in this direction, you can see that some lift will be generated from the bottom due to the pressure differences. So, like this we can have number of examples, real life examples, where this lift is very important. As I mentioned, some cases we want to generate the lift so that it will be useful in the application of that particular type of problem, just like in the case of aircraft, or in some cases we want to reduce the lift effect so that we will have a smooth operation, say for example with the movement of a car. So, you can see that whenever a lift is generated, the efficiency will be reduced, so that we want to reduce the lift effect on the car. So, like this number of examples we can have as far as lift is concerned. So, now before further discussing the lift effect with respect to the flow surrounding a cylinder or a airfoil, we will just briefly discuss another important parameter called circulation. So, the circulation effect we have discussed earlier when we discussed about the potential flow in the earlier lectures, but here with respect to the lift is concerned, we will be discussing more about the circulation. So, as far as circulation is concerned, say it is generally viewed as a mathematical concept, and the circulation is the line integral of the tangential component of the velocity around a closed fluid particle path. So, you can see that if we consider a fluid particle path like a closed fluid particle path like this, defined by this curve C, and then the circulation is the line integral of the tangential component of the velocity. So, the tangential component of the velocity V here around the closed fluid particle path. So, actually the circulation is a real physical quantity, and then if you can measure the velocity component, or with respect to the measured data, we can calculate the circulation. So, this circulation is, as you can see, it is a measure of the swell of the fluid flow. So, the circulation is coming from the rotational effect, or the, say with respect to the here you can see that we are considering a closed fluid particle path. So, it is generally considered as the measure of the swell of the fluid flow. So, and it represents the net vorticity in an area bounded by any closed path of the fluid particle. So, mathematically the circulation we can write as, mathematically the circulation can be represented as gamma is equal to, capital gamma is equal to the integral over the curve C V dot ds. So, where ds is the incremental arc length of a closed curve C as described in this figure. So, the mathematical expression for the circulation is capital gamma is equal to the integral over the curve C V dot ds, where V is this as we discussed, V is the velocity, the tangential component of the velocity as shown here in this figure. So, now with respect to this, the definition of the circulation. So, as we have seen in the case of potential flow when we discussed about the potential flow. So, if we consider the flow as irrotational, so as far as irrotational flow is concerned, we can see that we can write the velocity component V is equal to del phi. So, here this V is equal to del phi, and therefore, V dot ds is equal to del phi dot ds, and that is equal to d phi. So, that we can write, therefore, this circulation gamma is equal to integral over the closed path curve C d phi. So, we can see that this is equal to 0 for irrotational flow. So, generally we can say that as far as irrotational flow is concerned, the circulation will be 0, but you can see that as far as the circulation is concerned, within that closed curve which we consider, if there are singularities enclosed within the curve, then circulation may not be 0. So, if you consider, say for example, the circulation around a circular path, say if you consider as far as here is concerned, you can see that if you consider closed circular path like this, then you can see that here we will be having a free vortex V theta is equal to k by r, where k is a constant, and the circulation around the circular path of radius r for this case will be gamma is equal to integral 0 to 2 pi k by r d theta, where r is this radius defined here and theta is this angle, and ds is this, and here so gamma is equal to, you can see that it is 2 pi k. So, where k is a constant. So, here you can see that even though here what we consider is rotational flow and potential flow, but whenever there is a singularity or if singularities are there within that closed curve, then you can see that circulation will not be 0. So, we get a value for circulation gamma is equal to 2 pi k. So, this way we can see that this whatever we have discussed as far as circulation is concerned, say with respect to the lift coefficient or lift of the on the body, we will just discuss now how the circulation effect will be coming. We will discuss with respect to the case of a rotating cylinder. So, now let us compute the lift for the case of a flow over a rotating cylinder. So, here you can see here the cylinder is here, the cylinder is of radius r and it is rotating, and then a free stream velocity, free stream flow is coming, free stream velocity of v is in this direction. So, now this cylinder is also rotating in this direction. So, for this case, by let us assume the flow to be say the potential flow, so that we can apply the Bernoulli's equation between any point in the unaffected flow region, that means this region, and any point on the surface of the cylinder. Say particular point we consider on the cylinder, and then between we consider the pressure difference between any point on this fluid, that means outside unaffected flow region and any point on the surface of the cylinder. So, this case, so the pressure at any point on the cylinder we can derive as P is equal to P0 plus half rho v square minus half rho small v square, where rho P0 is the pressure in the uniform flow region at some distance ahead of the cylinder, and small v is the velocity at the cylinder periphery, and capital V is the free stream velocity. So, we can write the pressure at any point on the cylinder here at any particular point P. So, if we consider the P0 as the pressure outside the cylinder which is not affected, so that we can see here say P is equal to P0 plus half rho capital V square minus half rho small v square, where capital V is the free stream velocity and small v is the velocity at the cylinder periphery. So, now say we have seen the circulation aspect earlier. So, from the principle of circulation we can write, we can see that the velocity on the periphery, that means the velocity on the cylinder periphery, we can write as V is equal to 2 capital V sin theta plus this gamma circulation divided by 2 pi r. So, this we can get from the principle of circulation. So, here this is the case we consider, this is the rotating cylinder and free stream velocity or free stream flow with velocity capital V is this direction. So, the circulation around the cylinder when we consider, we can write the velocity at the cylinder periphery, V is small v is equal to 2 capital V sin theta plus gamma by 2 pi r. So, now if we use this expression in the previous expression which we have seen here, P is equal to P0 plus half rho v square minus half rho small v square. So, if you use this, then we get the pressure difference delta P is equal to P minus P0 is equal to half rho v square, half rho capital V square minus half rho into 2V sin theta plus gamma by 2 pi r whole square. So, where small v, we substituted for this small v here, which is equal to 2 capital V sin theta plus gamma by 2 pi r in this expression. So, we get the pressure difference delta P is equal to P minus P0, that is equal to half rho v square minus half rho into 2v sin theta plus gamma 2 pi r all square. Now, the lift DFL on an elementary surface area of the cylinder. So, if you consider in the previous figure here, if you consider the elemental surface area, then we can get this DFL can be written as DFL is equal to minus LR d theta delta P sin theta. So, this LR, L is the length of the cylinder, so R is the radius of the cylinder, LR d theta is the elementary surface area, and we will get the lift on the elementary area as DFL is equal to minus LR d theta delta P sin theta. So, we can see here with respect to this figure, if we consider this elementary area, and we get the, as far as lift is concerned, we get the expression as DFL is equal to minus LR d theta into delta P sin theta. So, here this negative sign is because of the pressure force always act towards the surface, and sin theta is always positive. So, finally, if we integrate, the lift force FL is equal to minus integral 0 to 2 pi LR d theta delta P sin theta. So, we get the lift force on the rotating cylinder FL is equal to minus integral 0 to 2 pi LR d theta delta P sin theta. So, this delta P we have already seen the value of delta P here. So, delta P is already defined here, and then substituting for delta P and simplifying, the lift force can be written as follows: FL is equal to rho V L into gamma. So, where the lift force on the cylinder FL is equal to rho V L gamma, where rho is the density of the fluid, capital V is the free stream velocity, L is the length of the cylinder, and gamma is the capital gamma is the circulation. So, this expression is called the Kutta-Zewski equation. So, this say expression are independently derived by Kutta and Zewski, and this expression is called the circulation. With respect to circulation, here the lift force on the cylinder equal to rho V L gamma. So, this Kutta-Zewski equation is one of the important equation, and Kutta and Zewski independently showed that for a body of any shape in 2-dimensional flow, the transverse force per unit length is rho V gamma, where V is the free stream velocity and gamma is the circulation and rho is the density of the fluid, and this force is perpendicular to the direction of V. So, this is one of the important expression as far as this lift is concerned, and then we can see that this Kutta-Zewski equation has got number of applications, like in the ship propulsion, and like that we can see many applications in the case of mechanical engineering also. So, Kutta-Zewski equation is one of the important equation, and this gives an expression for the lift force. So, as we have seen here in the previous slide, lift force is equal to rho V L T. So, if we consider unit length for, we have seen here for the case of a rotating cylinder, but they have shown that the body of any shape, and this equation is valid if we consider a 2-dimensional flow. So, that lift force is given as rho V gamma, where rho is the density of fluid, capital V is the free stream velocity, and gamma is the circulation. So, this Kutta-Zewski equation is one of the important equation, and number of applications are there. And another important aspect with respect to this circulation and lift force is called the Magnus effect. So, here if you consider either a rotating ball or a rotating cylinder like this, and a free stream flow is coming like this. So, this lift effect which we have discussed earlier. So, if there is circulation imposed upon a cylinder placed in uniform flow, it experiences a force, that is a lift force. So, this phenomenon of lift was first investigated by Heinrich Magnus in 1852, and this effect is called a Magnus effect. So, the free stream flow is coming, and if there is a circulation for the circular cylinder, as we can see. So, this effect is called a Magnus effect, and then this has also got number of applications. So, say for example, if you consider say either a cricket ball or tennis ball, and then say if there is no spin, if the ball is not spinning, we are just throwing like this, just throwing without spinning, then you can see that the effect is shown in this figure here. there is say there is no spin, so you can see that the body the ball is going like this, but you can see that if there is a spin, that means you are also while it is throwing, or if there is a flow and then also you are spinning the ball, then you can see that there will be a lift effect. There will be a lift effect that is called the Magnus effect. You can see that here it is shown in this figure here. So this is the ball and it is also rotating or it is spinning, so that whenever it moves you can see that this so called Magnus effect is there. So this effect is very important. You can see that when we play either cricket or tennis or golf or any of where we use balls like this, you can see that while throwing the ball or while batting the ball, if say a spinning is also provided, then you can see that there will be lifting effect other than the movement of the ball due to the spinning. So this so called Magnus effect is very important. We have to consider this effect in many cases, like when we play cricket or when we play tennis, like that. Say the spinning effect has got a lift effect on the ball. So that is very important in many of the problems. So we have to consider this Magnus effect. So now we have seen the lift force and lift coefficient with respect to the circulation, and also we have seen the Magnus effect. And now say with respect to this the circulation effect, when we consider the lift coefficient, we can write CL is equal to the lift force by area divided by half rho v square. So now if we consider the circulation also, then we can write this FL is equal to rho v L gamma, where v is the free stream velocity and L is the length of the cylinder which we consider, and gamma is the circulation. So this area is concerned, if we consider a cylinder, you can see that it will be 2 RL. So rho v L gamma by 2 RL divided by half rho v square. So that is equal to gamma by RV. So this is the lift coefficient CL, and now this is equal to, this is also equal to, now if you substitute for this gamma as say with respect to the earlier discussion, we can write gamma is also equal to 2 pi r Vc, where this small Vc is the velocity on the periphery of the cylinder. So 2 pi r Vc by Rv. So this is equal to 2 pi into Vc by capital V, where capital V is the free stream velocity. So finally the lift coefficient, we can show that it is a ratio, it is proportional to the velocity at the periphery of the cylinder divided by free stream velocity. So CL is proportional to Vc by capital V. So this Vc by V is the ratio, it is the ratio which affects the location of the stagnation point at the lower portion of the cylinder. So CL is a function of Vc by V, or it is proportional to Vc by V. So now you can see that when we analyze various cases, when this Vc by V is equal to 2, you can see that the stagnation point meet at the bottom of the cylinder, as in this case here, which is the limiting condition for this case. So we have already seen this Vc, that means the velocity on the periphery of the cylinder, Vc is equal to 2V sin theta, and this will be maximum when theta is equal to 90 degree. So if theta is equal to 90 degree, we can write Vc is equal to 2 into V. So hence we can write coefficient of lift, which we discussed the CL, here we have already discussed the CL will be equal to 2 pi. 2 pi is the, here we have seen that 2 pi into Vc by V. So Vc is equal to 2V, or Vc by V is equal to 2. So coefficient of lift is equal to 4 pi, which is equal to 12.56, and this is the theoretical maximum possible value of lift coefficient, say for the case which we consider as in the case of a rotating cylinder. So like this, for various other cases also we can check for the coefficient of lift with respect to the circulation effect. So now we have seen the coefficient of lift and the circulation, and the circulation effect on the lift force is concerned, and we have seen the case for the circular cylinder. So before further we discuss the case of an airfoil and its lift effect with respect to the circulation, we will just discuss a small example here. So, the example problem is a cylinder 1.4 meter of diameter is rotated about its axis in air having a velocity of 118 km per hour. A lift of 4686 Newton per meter length of the cylinder is developed on the body. Assuming ideal fluid flow theory, find A, the rotating speed, and B, the location of the stagnation point, and the fluid density is given, rho is equal to 1.24 kilogram per meter cube. So, now the problem here is we have got a rotating cylinder and the diameter of the cylinder is 1.4 meter as shown in this figure, and the free stream velocity is which is airflow, the free stream velocity is 118 kilometer per hour, and it is observed that the lift force is 4686 Newton in this direction. So, we have to find out the rotating speed of this cylinder and the location of the stagnation point for the problem. So, now as we discussed earlier, so with respect to the figure, we can use the Kutta-Jaworski equation here. So, that lift force is obtained as Fl is equal to rho v L gamma. So, here this already the lift force per unit length is given as 4686 Newton per meter, and rho is equal to 1.24 kilogram per meter cube. So, that we can get here this, we can find out gamma. So, before finding circulation gamma, we will convert this velocity, free stream velocity, in terms of meter per second. So, it is given as in the previous case, the airflow is 118 kilometer per hour. So, if we convert it into meter per second, 118 into 1000 by 3600 into meter per second, that is equal to 32.78 meter per second. So, now if we use this relationship, Fl is equal to rho v L gamma. So, that we will get 4686 is equal to 1.24 into 32.78 into circulation gamma. So, that we get the circulation gamma is equal to 115.28 meter square per second. But also we can see that in the case of a circular cylinder like this, gamma is equal to the velocity on the periphery V c into 2 pi r. So, and also we can see that V c is equal to r into omega, where the omega is the revolutions per minute rpm of the with respect to the, say, the omega is the angular velocity. So, with respect to the rpm, so V c is equal to, we can write r omega, where omega is the angular velocity. So, that is equal to 2 pi r n by 60, where n is the rpm revolutions per minute. So, that finally we get gamma is equal to 2 pi r whole square into n by 60. So, from which we can find out this number of revolutions per minute, n is equal to 357.57 rpm revolutions per minute. So, this gives the speed of the cylinder. So, now the second part of the question is we have to find out the stagnation point. So, here for this problem, here we want to get the location of stagnation point. So, we have already found the rotating speed. So, if you put the force to find out the stagnation point, we can see that the velocity on the periphery should be equal to 0. So, we can write V c is equal to 2 v sin theta plus gamma by 2 pi r, the circulation by 2 pi r, that should be equal to 0. So, here this r is equal to d by 2, that is equal to 0.7 meter. So, that we can write this expression we can equate to 0. So, 2 into 32.78 sin theta plus 115.28, which is the circulation we have already calculated, divided by 2 pi into 0.7, that is equal to 0. So, that finally we get sin theta value is minus 0.3998. So, theta is equal to minus 23.56 degree over 203.56. So, like this is a simple example. Like this, various other problems we can solve. So, by considering the problem with the circulation, same we have to consider the circulation effect, and then we have to use the Kutta-Jaworski equation, which we have derived earlier. So, this is the case, the lift force and the effect of circulation on the lift force. So, we have seen with respect to this example. So, now we will discuss in detail about the lift effect on an airfoil. So, let us consider the lift on an airfoil. So, if you consider an airfoil like this in this slide, you can see that the airfoil is oriented like this. So, there the alpha is the angle of attack, and if you consider C as the chord length, and you can see that the lift force effect is coming like this. So, if we use the Kutta-Jaworski equation, we can write, say if circulation is also considered, we can write FL is equal to rho L V gamma, where gamma is the circulation, that is equal to pi C into V sin alpha, where alpha is the angle of attack and C is the chord length and V is the free stream velocity. So, that finally we can write the lift force as far as this airfoil is concerned. We can write FL is equal to rho L V into pi C V sin alpha. So, that is equal to pi C into rho L V square sin alpha, where C is the chord length for the considered airfoil. So, now we generally express the lift effect with respect to the coefficient of lift. So, we will write the lift effect on the airfoil as the coefficient of lift. So, that we can write CL is equal to coefficient of lift is equal to FL, the lift force by area, divided by rho V square by 2. So, here for this airfoil is concerned, A is equal to C into L, where C is the chord length, and then we can write this can be put as. So, we have already derived FL is equal to pi C rho L V square sin alpha. So, we can substitute back here, and A is CL, we can put it back, and finally, we will get the coefficient of lift for the airfoil as 2 pi sin alpha. So, here we have derived the coefficient of lift for the airfoil. So, by considering the lift. So, here you can see that this only the coefficient of lift is only a function, 2 pi is 2 and pi are constants. So, only it is a function of the angle of attack. So, whenever you can see that this airfoil is placed in such a way that this alpha is equal to 0, then you can see that the coefficient of lift will be 0. So, lift will be also 0. So, to generate lift, we have to keep this at some angle. So, this angle of attack is the most important parameter as far as the airfoil is considered here. So, with respect to the airfoil which we analyzed just now, we can see the important parameters or the important factors affecting the lift are lift force on an airfoil is dependent upon the cross section shape of the airfoil. So, what is the shape of the airfoil which way we designed the airfoil, and then of course, the most important parameter is the angle of attack, and then the planned form size of the wing. So, if we consider the aircraft, then with respect to the airfoil which we discussed, so how we put the wing such a way that the planned form size of the wing. So, that has another important effect with respect to the lift, and then of course, the density of the air. So, since we have seen that the Kutta-Jaworski equation which we have seen earlier, you can see that FL is equal to rho L V gamma. So, this depends upon the density of the air and the velocity of the flight through the air. So, these are some of the important parameters or the which affect the lift. So, if you want to optimize the lift, so say for the maximum lift as far as the aircraft is concerned, we have to design in such a way that the shape of the airfoil should be optimized, and then the angle of attack whenever the aircraft is flying, then the angle of attack should be in such a way that it will get maximum lift, and then the planned form size, and then other important parameters are the density of the air, and then of course, the velocity of the air. So, based upon these parameters, we can optimize the design in such a way that we get the best effect as far as lift is concerned. So, now through experiments, we can conduct various experiments in the laboratory, and then we can observe the effect of this angle of attack on the, say for example, in the case of an airfoil. So, if you plot the angle of attack on the x axis, and then if you plot the coefficient of drag and coefficient of lift on the y axis, then you can see that this as far as coefficient of lift is concerned, you can see that it is going like this. Say whenever say here starting from this value, it is going like this, it is increasing, keep on increasing. So actually even the theoretical coefficient of lift is 2 pi sin alpha, which represent this line, but reality will be, you can see that it will be coming like this, and then we reach a maximum point or the point of maximum lift, where we define a point called start point, and then it reduces. So similarly the draft coefficient, you can see that it is going like this. So this, with respect to this, so this plot we can obtain through various experiments by placing the airfoil at different angles, and then we can get the we can plot the coefficient of drag and coefficient of lift. So now, as far as the lift on the airfoil is concerned, say the efficiency of the airfoil, you can see that is obtained as a ratio of coefficient of lift to coefficient of drag. So you can see that much higher compared to the rotating cylinder. So the rotating cylinder, which we have discussed earlier, if you compare with respect to the airfoil, which we discussed now, you can see that here CL by CD will be much higher, and at high angles of attack, in the case of airfoil, we can see that even best shaped airfoil is subjected to separation near leading edge. So due to the, say, when the angle of attack is higher, then you can see that, say, there will be separation near the leading edge, and when this happens, it is followed by rapid drop in the lift drag ratio, and this condition is called as stall. So here you can see that whenever we keep on increasing the angle of attack, so initially the coefficient of lift is increasing, and then it reaches a maximum point, and then you can see that after this there is a sudden drop as far as coefficient of lift is concerned, and this location, this condition is called as stall. So where the rapid drop in lift drag ratio takes place. So now, say, with respect to this, whatever we have discussed is, say, how the angle of attack is important as far as the design of the airfoil, and now we have seen that when it reaches, say, we cannot keep the angle of attack to say, after a certain limit, the coefficient of lift is decreasing, which we have seen the condition as stall. Now let us discuss more about the circulation effect as far as airfoil is concerned. So we have already seen the angle of attack effect as far as the airfoil is concerned. So but from the theories, we can see that for ideal fluid flow past an airfoil, as per lift theory, the calculated lift for an airfoil for non-zero angle of attack, actually theory says, the theory gives us 0, the calculated lift will be 0, but in reality you can see that lift is produced. So in reality the flow should pass smoothly over the top surface as below. So you can see that airfoil is placed here, even at an angle of attack there should be smooth flow over the top surface, and like this. But say this should be the condition, but you can see that due to the angle of, say, when we keep it as at an angle or the non-zero angle of attack, you can see here, but the actual flow is like this. So you can see that if this is the leading edge and airfoil is placed at an angle of attack, and then you can see that here the streamlines are plotted. So here this trailing edge is concerned, there is disturbance takes place at the trailing edge, and then same the actually due to the angle of attack here, actually what happens is there is a circulation is produced. So we can explain this lift effect. As we have seen that theoretically there should not be any lift, but actually lift is happening for the case of an airfoil placed at an angle of attack. So this we can explain with respect to the swirling flow around the airfoil. So you can see that since the airfoil is placed at an angle of attack, then say as described in the figure here, this at the trailing edge, then the stream, if you plot the streamline, then you can see the disturbance takes place, and then a swirl takes place with respect to the airfoil. So this adding of this swirl eliminates the unrealistic behavior near the trailing edge. So this phenomena of the lift with respect to the airfoil we can explain with respect to this swirl effect or the circulation effect. So the average velocity on the upper surface is increased, on the lower surface is say average velocity on the upper surface is increased, then in the lower surface say the effect is taking place, and as per the Bernoulli's equation we can see that the pressure at the upper surface is decreased and at lower surface is increased. So, the average velocity on the upper surface is increased and the lower surface it is decreased, and similarly the pressure at the upper surface is decreased and at the lower surface it is increased. So, that is with respect to the Swayam effect, and the net effect is to change the original zero lift condition to that of a lift producing airfoil. So, this is the way which we can explain what is really happening with respect to say when the airfoil is placed with respect to an angle of attack. So, if we consider the swirling effect with respect to the angle of attack, then we can see that say the velocity on the upper surface will be increased and then the lower surface will be decreased, and similarly the pressure at the upper surface is decreased and at the lower surface is increased. So, finally, this effect, the net effect is a change in the original zero lift condition, and then lift is produced as far as the airfoil is concerned. So, this effect we can explain with respect to this figure here. So, this clockwise swirl is actually the circulation which we discussed earlier. So, if you consider say here the airfoil at an angle of attack and the free stream velocity is coming. So, here this disturbance takes place at the trailing edge, and then if you add this the circulation effect or the swirl effect which we have discussed here. So, here this is the airfoil with respect to the flow and the disturbance, and then plus so here this effect of circulation takes place, and finally the resultant flow is say with respect to the finally if you add together then the resultant flow will be like this, and then finally we can see that lift is produced. So, here say even though theoretically as far as airfoil is concerned there may not be lift, but practically what happens is that say this at the trailing edge the disturbance takes place, and finally we will be considering the circulation effect, and then finally the flow will be like this. So, this way we can explain the lift effect coming on an airfoil. So, this effect of circulation around the airfoil, so you can see that the average pressure on the lower surface is greater than that on the upper surface, and this pressure difference will cause some of the fluid to attempt to migrate from the lower to the upper surface, and finally a trailing vortex will be formed from each wing tip. So, if we consider the aircraft wing, then what happens is that so this due to this pressure difference, then some of the fluid will be migrating to from the lower to the upper surface, and then finally trailing vortex will be formed from each wing tip, and then the trailing vortices are connected by the bound vortex along the length of the wing. So, here you can see that the vortex how it is generated with respect to circulation. So, here this is the wing of the aircraft, then you can see that the free stream the airflow is in this direction, and here you can see the formation of the bound vortex, and then also you can see that a trailing vortex will be formed at the this is the trailing vortex here, and this location this is the trailing vortex, and similar way this side also, and finally the bound vortex generates the circulation that produces the lift effect as far as the aircraft wing is concerned. So, this we can show with respect to the airfoil theory, airfoil the lift on the airfoil and the circulation effect which we have discussed earlier. So, now if you consider instead of the airfoil, if you consider the circulation around a circular cylinder which we discussed earlier, then you can see that this is the cylinder here, and then the free stream velocity is coming, and if you plot the streamlines, so flow without circulation will be like this, that means the cylinder is not rotating. So, here if you the flow without circulation is going like this, but if the cylinder is also rotating, that means flow with the circulation is, you can see that what is the effect happening here. You can see the changes in the pattern of the streamlines, and this figure is taken from this website here put here. So, the circulation around a circular cylinder without circulation, that means here there is no circulation effect, and flow with the circulation. So, the magnitude of the lifting force per unit length of the cylinder, as we have discussed, FL is equal to rho V gamma, where gamma is the circulation and rho is the density of the fluid, v is the free stream velocity, and say for no slip boundary condition, as we have discussed, gamma is equal to integral v dl, which results in gamma is equal to v into 2 pi r, where v is the velocity at a point on the surface and r is the radius of cylinder. And finally, we can write Fl is equal to rho v 2 pi omega r square, as v is equal to omega r, where omega is the angular velocity and r is the radius of the cylinder. So, this effect we can see here. So far we have seen the lift force and the coefficient of lift, and then the importance of circulation. So, we have seen in the case where if a cylinder is rotating or if not rotating, what are the effects, that means with respect to circulation, the flow, and with respect to circulation. And also we have seen an airfoil with say 0 angle of attack, there is no lift effect, but when there is an angle of attack is there, then there is lift effect is there. So, that what is the theory behind that we have discussed, and also we have seen the various aspects like Magnus effect, that means when we say spin a ball, say for example the case of cricket, when we spin the ball, and then or tennis, when we spin the ball, then what will be the effect? There will be a lift effect, and then it will be due to the spinning effect and the lift effect, it will be very difficult to predict which direction the ball will be moving. So, that is the effect of this the rotating or spinning effect, or the so called circulation effect as far as lift is concerned. So, with this chapter, say we are closing this chapter on the boundary layer theories and drag and lift effect. To summarize, so in this chapter we have initially discussed the various the kinds of external flows, and then we are differentiated with respect to the internal flows, and then also we have seen the boundary layer formation, boundary layer theories, Prandtl's and Karman's theory, and then also various solutions with respect to the boundary layer theories, say for various parameters like the shear stress, and then the velocity as various locations, and then the say we have also seen that the boundary layer is concerned say with respect to the flow over a flat plate. We have seen initially it may be laminar, and then there will be transition, and then finally turbulent stage is achieved. So, all this with respect to the boundary layer theory we have discussed, and also the boundary layer separation and wake formation also we have discussed in this chapter, and also the theory behind the drag and lift we have discussed in detail, the drag force and then coefficient of drag, and then to calculate this drag force and coefficient of drag for various cases whenever the flow is laminar, or the boundary layer is laminar, or boundary layer is turbulent. And also we have seen its importance, the importance of drag as far as say in the design of various say various problems like automobile industry, in the design of cars, or the design of say bus, or various other kinds of design. And then this lecture we have discussed the lift force, and then the coefficient of lift, and the circulation effect as far as lift is concerned. So, with this the external flows here we have discussed, and now in the final chapter we will be discussing the internal flows or the pipe flow, that we will be discussing in the next lecture.